Welcome to your podcast for part 2 of lesson 32. So we talked about this in class a little bit, but whenever we work with inclined planes, we're just going to take that normal X and Y axis that we are used to working with that go completely in the horizontal and vertical direction, and we're just going to tilt it up at some angle. So that when we do, you have your x-axis, which is parallel to that contact surface, and your y-axis now is going to be going at a right angle or perpendicular to that contact surface. Initially on these problems we are going to ignore friction. So for this problem the only forces acting on the block are its weight and also the normal force. We know weight is going to act straight down towards the center of Earth, so here's our FW. And normal force we know is going to be acting perpendicular to the contact surface. So if we just kind of draw a dotted line that runs parallel to that contact surface, we can very easily draw in our normal force, again making that right angle, okay, or 90-degree angle perpendicular to that contact surface. Since those two forces do not cancel each other out, the block is going to accelerate down the incline, so we'll see acceleration in that direction. Okay, so to find the net force acting on the block, we need to split the forces into purely x and y components, which will allow us to simplify this drawing. So exactly like we did in the last couple lessons. Keep in mind that we've redrawn our new coordinate system, so we've got our y-axis, which is perpendicular to that contact surface. And so for this problem, our normal force, or Fn, is completely in that y direction. So the only thing that we need to worry about taking care of is the FW. So we've got our force of weight, which again we know acted straight down, and we can take that and find its x and its y components, and I'm just going to call that FWX and FWY. Alright, when we look at this problem, we know that the block is not accelerating in the y direction at all, and what that tells us is that our normal force and our y component for its weight have to be equal and opposite to each other. Okay? And because those two things are equal and opposite, they're going to cancel each other out. So now the only force that we have acting on that block, okay, is our FWX. Okay, or FWX. Since that's the only force that's acting on the block, we know that that is our net force. And this should make sense because if you go back to what we learned in our last couple lessons, the acceleration of an object is going to be in the direction of the net force. We know that this block is going to accelerate down the ramp, and that is caused again by the F net, which is equal to our FWX. So what does FWX equal? Well, we know that FWX is equal to F net, and we know that F net is equal to mass times acceleration. And so I can solve for the acceleration of the cart by taking FWX and dividing it by the mass. So depending on what information you have, whether you're given this particular angle or whether you're given the actual acceleration and you're solving for the angle, you'll be able to substitute in different equations that we've learned over the last couple lessons. And so let's take a look at that on the next couple slides. Practice problem number 1 asks us to solve for the acceleration of a cart rolling down a plane that is inclined at 30 degrees. So there's our 30-degree angle. And what we can do is extend our coordinate system here to run through our object. Okay, so we've got our x and our y. We know that our force of weight is going to act straight down because gravity acts towards the center of Earth. And we know that our normal force is going to act perpendicular to that contact surface. Okay? What we learned to do yesterday is now take this FW, since it's not going in the X or Y direction, and I need to find its X and Y components. So there's FWX, okay, and FWY. Okay. And we know that in the Y direction, we have an overall net of 0. And so what that tells me is that my normal force is equal and opposite to FWY. So since they're equal in magnitude but opposite in direction, they will cancel each other out. And so the only net force that I have acting on this object then is my X component for weight. Okay, and using what we've learned in geometry class, we know that if my inclined plane is at a 30-degree angle, that this angle in between our FW and FWY is going to be 30 degrees as well. Since that's 30 degrees, I know that the side opposite of that is equal to our FWX. And so I can use the sine of 30 and set that equal to my opposite, FWX, divided by my hypotenuse, which in this case would be FW. When I rearrange this, I know that FW then times the sine of 30 is going to be equal to FWX. Okay? Now here's when I can start to substitute in some values. We know that Fnet is equal to FWX, and we also know that Fnet is equal to MA. Using SOHCAHTOA then, I can substitute in FW sine of 30 for Fx and set that equal to MA. And I know from Newton's first law that Fw is also equal to mg. So I can substitute in mg for Fw multiplied by the sine of 30 equals ma. Okay. And again, remember, my ultimate goal is to solve for acceleration. So if I divide each side by mass, that will cancel out. And so I'm left with 10 multiplied by the sine of 30, which is equal to my acceleration. The sine of 30 is 1/2, so 10 times 1/2 is 5 meters per second squared for my acceleration of this cart rolling down an inclined plane at 30 degrees. In example number 2, we're asked to solve for the normal force acting on a 2-kilogram cart rolling down an inclined plane at 30 degrees. And so we know our 30-degree angle is there, and we can add in our x and y coordinates. Fw, again, we know is going to act straight down. And since we know that this is a 2-kilogram cart, we know that Fw is equal to mg, which is going to be equal to 2 times 10, or 20 newtons for our Fw. I know that my normal force, I can draw in, it's acting perpendicular to that contact surface, and I know that I'm going to have to take my Fw and find its x component and also its y component. Okay. Now again, we know that because the cart is not moving up and down vertically on this track, or in the y direction on this track, we know that our normal force is equal in magnitude but opposite in direction to Fwy. Okay. Since we know that angle of the ramp is at 30 degrees, again, that lets us know this angle here is 30 degrees. Okay. Once I know that, I can use SOHCAHTOA to find my value for Fwy. Fwy is adjacent to this 30-degree angle, and so I would use cosine of 30, and that's equal to the adjacent side, Fwy, divided by the hypotenuse, right, directly across from that right triangle, would be Fw. Okay. I'm going to substitute in my 20 newtons that I've solved for FW. Okay, and when I rearrange this equation, that's going to give me 20 newtons times the cosine of 30, and that's equal to FWY. And when you plug this into your computer, or your calculator rather, and you round, you are going to get 17.3 newtons, which is equal to your FWY. Again, since we know that that's equal, you know your value for Fn, which is equal in magnitude but opposite in direction, okay, is also going to be equal to that 17.3 newtons. In this problem, we are asked to find the angle of this incline if that cart is now accelerating down that ramp with a rate of 2 meters per second squared. Okay. And so just like in the other problems, I'm going to draw my x and y axis in here. I know that my FW is going to act straight down, and my normal force is going to be perpendicular to the contact surface. Okay. I know again that my FWX and FWY are going to be acting in the complete x and y directions, and I know that the angle that that incline is at is equal to this angle right here. Okay, so that is our theta. Okay. There's no acceleration in the y direction, so again what that tells me is that my normal force is equal and opposite to my FWY. So the only force then that's acting on this, or my F net, is going to be equal to FWX. And we know that that's equal to its mass times its acceleration. So again, now we can start to substitute in some different equations that we've learned through the last couple lessons. We know that FW is equal to mg, and since we're solving for this angle here, this side of our triangle is equal to FX, or FWX, sorry, which is opposite of our angle that we're trying to solve for. So I know that sine of theta, whatever that angle is equal to the opposite FWX divided by the hypotenuse, which is FW. I'm going to substitute MA, mass times acceleration, in for FWX, and I'm going to substitute mg in for FW. The masses will cancel out, and so that leaves me with the sine of theta is equal to A over G. Both of these values I know. Okay. And so when I plug this into my calculator, I have the inverse of sine being equal to my acceleration, which for this problem was given to me at 2 meters per second squared, divided by my value for G, 2 meters per second squared. Okay. And when you plug and chug this into your calculator, you get 11.5 degrees.